Good afternoon, everyone. This is the last session of the preschool of this third volume of the ML for Health, and we'll have two physics seminar not related to ML directly, but here we will have two experts, both from first Raghunath Sahu, followed by Satviki Bhattacharya. They will talk about the uses of ML, like Partho did, and Partho did for phenomenology, and Rajesh did for gravitational wave. So here are some other use cases that the experts in the field that we have in our community will talk about. Some of you are already working in these fields, and some of you, this is the best opportunity to learn about a field that you have not exposed to. So Professor Raghunath Sahu is a professor in IIT Indore, and his expertise is in the field of quark-gluon plasma and other jets and all the stuff that he works on through media and all. So he will talk about how machine learning can help us uh, get more traction in our understanding of the subject. So over to Raghunath.
Okay, so thank you for the uh, introduction, and I'm quite happy today because this is the third version of ML for HEP, and this series of schools started in a time when, surprisingly, the machine learning, the physics Nobel Prize last year was given for machine learning. Although machine learning is not a new tool to physicists, it is age-old tool for physicists. But when it is getting a boost because of large volume of data availability across many disciplines, this is the right time to train the Indian researchers in the field of machine learning. And I must take this opportunity to thank all the organizers associated with this series of schools. Last school I attended in Bangalore. So it is a marvelous job our colleagues are doing. I think this will benefit our next generation researchers. So with this, let me directly go to the task today. So what I have chosen is, I believe it is a preschool. So preschool, the aim should be to expose to a broad audience, because high energy physics to other people, it is a branch of physics, but within high energy physics, there are many sub branches. And in the era of interdisciplinarity in science or technology, so I believe that everybody should have a equal opportunity or good exposure to uh, the science and technology beyond their subdomains. That is what I believe. And this is a good opportunity in the part of the preschool. So we get proper exposure to different areas and try to see where machine learning is can be applied. So with this, I will start with a little bit of introduction to quark-gluon plasma. And although I have written Large Hadron Collider, I may not go deeper into the Large Hadron Collider. And I will finish my lecture with two problems I have chosen for machine learning. Of course, you will have a hands-on machine learning in the main school and the workshop. So I believe that this should give a good exposure first. So I have made it very simple, and then we go to machine learning part. And I think everybody should not get bored with the type of subject I have chosen here. And another thing is, in a typical in-person classroom, the way we can actually change our navigation looking into your absorption level, that I cannot do. In fact, only I can see my screen, even my camera is not showing myself also. So in that way, please interrupt me if you um are getting bored, or the content is going on top of the head, or I am not audible. So any problem you are facing, you can give me a call through Ritesh, or you can also interrupt me anyway. So let me start with the discovery of subatomic particle. As everybody knows, in 1897, electron was first discovered as universally present in all elements, and that has actually stayed as one of the elementary particles so far. So when I say elementary particle, so what I mean is there is no substructure discovered within the range of energy available to us. We do not know if tomorrow we may discover a substructure of electron with the advent of more energy, but so far as of today, there is no substructure which is probed for electron. So this discovery started with J.J. Thomson, 1897. So he got Nobel Prize, and as you can see, like any area, so our particle physics or subatomic physics has a long history, and we went on up to the last big discovery of a Higgs boson in 2012 at the Large Hadron Collider, which brought L'Oreal in terms of breakthrough prize of this year. Of course, the theoretical contribution of Peter Higgs and Francois Enlert, so they got Nobel Prize in the subsequent year, I think 13. And this is our history of subatomic particles. And if you look at this artificial disintegration of atoms, ushered the machine age of nuclear physics, and that established the regime of atom smashing. Of course, this started from Cambridge, and now we are at CERN, and this will fascinate you when you know that Cavendish laboratory in Cambridge in 1932, where the first artificial disintegration of atom happened through bombardment of proton on lithium target, giving you 2 helium. This was done using the accelerator. And the whole game of accelerator and smashing atoms started from a 30 centimeter length cathode ray tube. And now we are operating the world's largest collider experiment at CERN, the European Laboratory for Particle Physics, where we collide lead ions, fully stripped lead ions, on lead ions, or proton and proton at TeV energies. And as everybody knows, twenty-seven is the periphery of the accelerator. So this is a view of the accelerator, and you can see age of science and technology. And if you analyze what is the need of this big accelerator, you will convince from the physics background. So there is a need of going for this sort of big accelerator. And this makes a slow transition from nuclear to atomic degrees of freedom, which are otherwise not available in nature because of the strong interaction properties, which I will come back. So now the journey from electrons to quarks is started with a really fundamental principle of optics, which tells me that lambda is equal to h over p. If I want to probe lower in length scale, I should use high in momentum or energy. And this essentially talked about the discovery, the need of high energies for discovering the particles or the quanta of the matter, like quarks and gluons. So, in the deep inelastic scattering at Stanford Linear Accelerator, for which the accelerator length was 3.2 kilometers, we could achieve electron positron energies up to 50 GeV. This is just a guideline. And if you want to probe inside the proton, so you can take actually the charge radius of proton, and you can calculate using the simple formula of de Broglie, which comes from the fundamental or the first principle of optics. You will convince yourself that if I want to probe a femtometer scale, I need either GeV or TeV energies. This is very fundamental. And through this, so we discovered different families of quarks and leptons, which are believed to be the fundamental or the basic constituent of matter. So far, we have up, down, charm, strange, and top, bottom. Similarly, the lepton category. And if you look at our experimental data and the theoretical predictions also, you will find the strong coupling constant for which the mathematical formula is this. You will find this is a running coupling constant because this depends upon the momentum scale, momentum transfer scale. So you will find this alpha s has a variation with the momentum transfer q. If I go to high momentum transfer, this alpha s is becoming smaller and smaller, and this is a typical property of QCD, the quantum chromodynamics. This coupling becomes weaker as the momentum transfer increases. As we go smaller in length, so my previous formula tells me that once I probe the lower length scale, so I need higher energies, and this will tell me that I go to small distance, patterns will move freely. This is the property of QCD, which is called asymptotic freedom. So these patterns, quarks and gluons, which are collectively known as patterns, so those are asymptotically free, asymptotic limit of energy or momentum. And as we enter to the inter quark distance separation being increased, the strong coupling constant will grow faster, as you can see here, and this will make quarks confined in the case of hadrons. This is called confinement, quark confinement. And this asymptotic property and infrared slavery is an inbuilt property of QUD, or the strong interaction. Thereby, this tells me that there is no free quarks or gluons or collectively patterns following Richard Feynman. So those are not seen in nature. So now, before I go to the curious mind of scientists, let me put up the analogy and differences between QD and QCD. So this is essentially the simplest atom. This is a hydrogen atom. So one electron is revolving around the nucleus. If I want to separate electron from this, simply I have to give 13.6 electron volt, and I am in a position to see H plus, which is essentially a proton, and a electron being separated. And this whole property is governed by quantum electrodynamics. Whereas if you look at quantum chromodynamics, so the situation is completely different because of the typical properties of quark confinement. So now you can see I have cased the three colored objects which are constituent quarks of proton, and as a whole proton is white in nature. And I should mention that this color has nothing to do with the real color. This is an intrinsic property of the quantum number associated with patterns. So now once I go ahead in separating these quarks, so the color field will increase. This will grow with separation. This is essentially followed from the fundamental principle of QCD potential. And what we will find is the quark and antiquark pair, those will be created from the vacuum. And instead of separating those two quarks, one quark will be combined with the other two quarks, forming a baryon, which is a three quark combination. And the vacuum created antiquark will be combined with the quark, creating a quark antiquark pair, which in particle physics language is called as a meson. So depending upon the quark type, it can be a proton, it can be a pi meson. So now what I showed you through this cartoon or the simulation, that QCD or the strong interaction has a different dynamics compared to QED or the quantum electrodynamics. So now the question is, can we find free quarks in nature? Because your QCD is telling me that free quarks finding in nature is not possible. So people predicted this 1973 asymptotic freedom by Gross, Wilczek, and Politzer, and later on also very important works by Cabibbo, Parisi, and Collin and Perry. Parisi got Nobel Prize later on for his multi-directional contribution to science, physics in particular. And 2004 Nobel Prize was given through these three gentlemen for their conjecture of asymptotic freedom. And going beyond this, the high temperature QCD tells me that normal nuclear matter undergoes a phase transition to quark-gluon plasma under extreme temperature and energy densities. In my discussion here, I plan to explain you what is called extreme temperature and energy density. And as you can see in this cartoon also, the hadron is essentially a caged part. The partons are caged inside the hadrons, and you can see this is a hadron gas, and many people use hadron resonance gas models to describe the behavior of hadron gas. And you can see, if at all we can form a plasma of quarks and gluons. Similarly, the way we create a plasma of electromagnetic plasma, so we can go on increasing the energy and stripping out the constituents. So possibly we can form a plasma of quarks and gluons. And the way it is scientifically defined is, it is a locally thermally equilibrated state of matter in which quarks and gluons are deconfined from hadrons. These are hadrons, so that this color degrees of freedom become manifest over nuclei rather than merely nucleonic volume. So these color degrees of freedom are prevalent inside the hadronic volume that is known to us, whereas quark-gluon plasma is defined in a way, so this color degrees of freedom manifests over beyond the nuclear volume. So this is the definition coming out after the discovery of quark-gluon plasma in the relativistic heavy ion collider in Brookhaven National Laboratory. So now the take-home message is, the QCD, high temperature QCD predicts that we can produce a quark-gluon plasma in the laboratory, be it a short-lived plasma of around 10 to the power minus 23 second lifetime, but we can produce in the laboratory. And this led us a journey to the beginning of the universe. And I will explain how this is taking me to the beginning of the universe. Before that, let me explain the fundamental difference between classical and relativistic collisions. Essentially, I borrow from the textbook of Griffiths. So you will find this is a two-body collision, and in the final state, we produce C plus B, D, and W is not produced. Essentially, I produced, this is a two-body final state, and this is a classical collision. So you can find the very beautiful discussion in particle physics, Griffith's book. And in our relativistic collision, what we people do is, we look at the multi-particle final state, we accelerate these projectiles, collide with the target, or in a collider mode, we accelerate both the projectile and the target, making the collision so vibrant. So the final state produces multitude of particles instead of the two-body final state. So these are called vibrant relativistic collisions, where we know that mass is not conserved. These are explosive collisions. Okay. And going ahead, so I must explain here that the collider experiments are more chosen, because mathematically you can show that we are more interested in the debris of the collision, and the debris is less, or the severity of the damage is less, if you go for uh, a fixed target collision, which is shown here in this cartoon, compared to a collider experiment where head-on collision happens in a free way when both the cars or both the particles are in motion. So here the debris is higher, or the damage is higher. This is governed by, a back of the calculation, back of the envelope calculation. You can show in the laboratory frame, your fixed target frame, your energy available for particle production goes like square root of the beam energy. Whereas in the center of mass frame, which is a collider frame, your center of mass energy goes like twice of the beam energy. That means more energy is available for particle production in a collider experiment in comparison with the fixed target experiment. So this is preferred. And fixed target experiment has its own advantage of achieving higher luminosity. That is why the next generation experiment, which is coming in GSI, with fair experiment, so that is a fixed target experiment. Of course, I will not discuss about those things in this presentation. And this is the way actually we make heavy ion collisions. This is a cartoon to show you that the Lorentz contracted heavy nuclei, so with a almost close to speed of light, so they are getting collided, and in the final state, the debris is essentially the produced particles from the system. And this takes me, I claim that this takes me to the Big Bang collision or early universe scenario, almost 13.7 billion years ago. So this is where we stand now, and it takes me to the early universe scenario. So mathematically or from the experimental perspective, I have the task of justifying that yes, I have taken you to a domain of energy density or temperature which prevailed at the beginning of the universe during the Big Bang collision. So this is the history of universe, and you can see our windows to the universe is through this accelerator, the Large Hadron Collider, the largest one on Earth, and this creates essentially the plasma of quarks and gluons, and the energy and temperature pertains to the domain where the universe was a microsecond old universe. That means it was almost 10 to the power 7, 13.7 billion years ago. And if you look at the relativistic heavy ion collisions, so this shows that two Lorentz contracted objects because of the relativistic speed, so they collide. After the collision, so this domain is called the collision overlap region, and these nucleons are called participant nucleons. These are called spectator nucleons. They are not participating in the collision domain. After this, there may be a pre-equilibrium dynamics which needs a proper probe, and there is a initial density deposited, and once a heavy initial density deposition is there, so there will be a huge pressure gradient driving the whole plasma to expand and cool down with time. And the quanta of the system at the moment is not known to me. I need a probe to understand if I have formed a plasma of quarks and gluons. So now the energy density being higher, this will actually develop a pressure gradient so that the whole expansion of the fireball happens. Possibly, let me put quote and unquote, possibly there is a QGP phase which needs a probe, and after the quark gluon plasma phase is formed, so this is very transitory in nature, and there will be a formation of hadrons out of these quarks and gluons. So this process is called hadronization. After hadronization, so we form a hadron resonance gas or hadron gas phase, and there will be a time where the mean free path of the system will be higher compared to their collision or the system size. So what we'll find is these final state particles, the pions, kaons, protons, so they will come out without being transferring momentum between them, and that is called the kinetic phase out. And at the detector level, which is sitting at a particular phase space, so you will find that these final state particles are captured or detected by these dedicated multi-purpose detectors sitting at different collision points in the Large Hadron Collider. So this is the space-time evolution of relativistic heavy ion collision. And you may ask me how much high is the high energy, and believe me that very small equations can explain you. Since I am probing low in the length scale, I need more energy, and more energy, immediately Einstein will jump in saying that if you allow me having more energy, I will have a multitude of particles formed in the final state, and that will be governed by this conversion of E to mc square. Again, this will be a early universe scenario, because once you have high energy because of the low length scale, you produce very high temperature in the system, and this high temperature pertains to the early universe scenario. So what I am doing is at the relativistic heavy ion collider in the Large Hadron Collider. So what we do is to probe the subatomic universe, we need very high energies which could produce multitude of particles in the final state, and this very high temperature will take me to the early universe. How do I do this? So I showed you uh, the collision dynamics, how we produce more particles in the system. Now you may ask, how many particles do I produce or create? Knowingly, I have written here produce, and I have crossed it saying that we create particles, we will not produce. So production is left to God. So that is not my term, it is termed by the Pope of the Vatican when he visited the Large Hadron Collider. So production is essentially reserved for the God, and this creation, or we create more particles, that is for the scientist. So now what you see here is multitude of particles. All these particles can be formed in the collision. But now each particle interaction with the dedicated detectors or the multi-purpose detectors sitting at different part of the phase space is completely different. Do you think that all these particles can go up to your detector level? Answer is no. So you can calculate depending upon this track length. Okay, before a particle decays, so this track length can be calculated from the C tau, and you will find depending upon their lifetime only 8 particles and their antiparticles can come up to the detector level. Those are gammas, proton, neutron, E plus E minus, muons, pions, and kaons, and hardly you will find K zeros, essentially K short and K long. Those are also measured from pion kaon channels. So now I have a big task in hand. I have to determine in particle physics the properties of all these particles and search for new particles, sometimes beyond standard model particles. And only I have given with the, to my liberty, it is given that, only 8 particles and antiparticles come to my detector level. So, as a particle physicist or high energy physicist, the task in hand is much more difficult the way people see, because from these particles which can fly up to your detector, you have to find already so many hundreds of particles. That is why the way people think in the tabletop experiments, high energy physics, the challenges in hand is much more. So now how many particles you produce in the final state? Just to tell you that we produce almost in the integrated form 20,000 particles in the phase space. And this also creates a new domain of applying statistical mechanics in quark gluon plasma or in this kind of high multiplicity environment. This is a plot to show you that the charge particle multiplicity density in the pseudo rapidity plotted as a function of eta, which is pseudo rapidity, and you will learn slowly why pseudo rapidity is taken. Otherwise, you may be knowing already also. So this is a central collision where more number of participants are participating in the collision, and we expect more number of particles to be formed. So compared to a peripheral collision where less number of particle formation is expected. So now we see expected behavior in our experiment. And if you see this multi-particle production follows the statistical behavior, because I promised you that I have to explain you that we go to a domain where there is an extreme condition of temperature and energy density. If that is the situation, I should be in a position to determine the temperature of the system. So temperature, the way it is measured, I do not have a thermometer at my disposal which I can put to quark gluon plasma and measure the temperature. This is simply I am expecting to produce a very high temperature environment where protons will melt. And you look at your material object, which is essentially the thermometer. So general thermometer will not work. So before applying the scientific tools, so let me tell you that the average population of particles follows a Boltzmann kind of behavior. You can see the Boltzmann killing factor sitting here, and the heavy particle yield should drop down because of the Boltzmann killing factor sitting in the denominator. That is what we see in the experiment. If you see pion number is higher, pion is the lightest boson or lightest particle, lightest boson produced in the multi-hadron production scenario. And if you go to higher and higher mass, you will find there is a decrease in the yield. So omega is much higher in mass compared to pions. That is why omega yield is lower. And very easily I can fit to a function which is Boltzmann in nature. And you may ask the question to yourself, when pion is a boson and if I go to baryons which can be fermions, how do I apply Boltzmann statistics instead of going to Fermi-Dirac or Bose-Einstein statistics? So this question I am leaving to you to think, derive mathematically, and convince yourself that high temperature QCD is more or less a classical object, a classical behavior. So with this, I am not taking you to the domain of particle production versus sub PQCD versus processes, or non-PQCD processes. and how that deviates from a thermalized Boltzmann distribution versus how a Levi-Salis kind of behavior is nowadays followed by this particle spectra. I'll omit these discussions because I have to focus on possible application of machine learning. So now what you see here is the photon spectra and quark gluon plasma temperature. So the invariant yield of direct photons coming directly, because photon mean free path is huge, because that is electromagnetic interaction exchange particle. It will hardly interact in the system, which is a QCD plasma. It will carry the temperature of the plasma without any aberration. If I look at direct photon yield, you can see a Boltzmann spectrum is function is fitted here. A exponential minus Pt, the transverse momentum, divided by T effective, the effective temperature of the plasma. And this inverse slope of the plasma will tell me that this is the effective temperature, and the temperature effective is coming out to be 300 MeV. And if you go to conversion, 1 EV is this much of Kelvin, you will find the temperature which is created while forming quark gluon plasma is essentially 10 to the power 5 times the core of the sun temperature, where we expect a electromagnetic plasma inside the core of the sun temperature. So this temperature is 10 to the power 5 times higher than the core of the temperature. And this temperature is measured from our knowledge of statistical mechanics application to this multi-Harton production dynamics. Now, after convincing you that we created very high temperature, which is actually telling me, this can melt the protons to produce a plasma of quarks and gluons. Let me estimate from the particle density in the phase space. Let me estimate the energy density. So this cannot be done directly. I have to rely on this seminal paper of Bjorken, written in 1983. So this essentially relies on a boost invariant hydrodynamic behavior at the mid rapidity, and the derived formula is Bjorken energy density is essentially related to the initial energy density of the plasma, and this is nothing but the transverse energy density in the phase space, in the rapidity phase, and divided with the fireball transverse overlap area pi r square. Tau is the formation time, and this can be converted to the mean energy or mean MT of the particles and 3 by 2 of the charged particles. So this conversion is necessary because detecting charged particles in our detectors are easier, and I have a good control on charged particle detection. And if I convert these two charged particles and I measure this mean energy of the particles, so I can estimate the initial energy density of the plasma, and you can see that the predicted value of energy density which is produced at the Large Hadron Collider is almost 16 GeV per Fermi cube. Of course, it is written in a way that your tau, which is not determined experimentally, can be assumed to be 1. Of course, at high energies the number will be low, and since it is sitting at the denominator, this will further increase. And by putting this 16 GeV, what I'm saying is this is the lower estimate, the lower bound of the energy density. And if at all we are producing the energy density, that's much higher because tau is a fraction and sitting at the denominator. So the prediction at Large Hadron Collider is very huge, and I should remind you here the energy density of a proton is around 0.17 GeV per Fermi cube. So this is much higher than the proton energy density. And if you look at the experiment, this Bjorken energy density multiplied by the formation time is now plotted as n part. N part is essentially, I showed you the number of participant nucleons, and you can find the head-on lead-lead collision, it produces more energy density compared to proton-proton. And of course, proton-proton within the error bar, you can see that also produces an energy density which is higher than 1 GeV per Fermi cube. And this 1 GeV per Fermi cube is an important number because the lattice QCD, the theoretical prediction tells me that if I'm going faster, you can actually tell me, because sometimes little bit of cross area should not make me off in my understanding. Okay. So you can actually disturb me if I'm going little faster because I do not see you. So this 1 GB per Fermi-Q is a number which is essentially telling me from the lattice QCD calculation, which is a theoretical calculation, that a quark hadron deconfinement transition can happen after 1 GB per Fermi-Q energy density. So that means at Large Hadron Collider, I am showing the data of ALICE. Similar data is also available from CMS, Atlas, and LHCb, which are big experiments. And what I'm showing you here is even the PP collision and up to the heavy ion collision, the lead-lead collision. In all sort of collisions at the Large Hadron Collider, I produce the basic requirement of a quark-gluon plasma energy density, which is predicted by the lattice QCD. This is the famous QCD phase diagram. So where the temperature is plotted by the sometimes baryon density, sometimes normal nuclear matter density scaled value. And what is very important here to note is this side is quark-gluon plasma, this is hadron gas. This is separated by a phase transition line, which is first order. This ends up with a possible, I put it as quote unquote because this is not yet discovered, and this may lead to a Nobel Prize or breakthrough prize when it is coming up with the critical endpoint in the phase diagram. And this goes to a second order crossover transition here, and this is the QCD phase diagram. And the lattice QCD calculation which I discussed with you is essentially telling me the energy density is scaled to T4, which is purely statistical in nature. This is essentially giving me the effective degrees of freedom of the system is plotted in the y-axis as a function of scaled temperature T by Tc, where Tc is my critical temperature of the plasma, and T by Tc1 is essentially the criticality happening here. You can see here there is an abrupt change in the degrees of freedom of the system, and I can easily explain you here. If you take a pion gas, which is a pure hadron gas, I have three isospin degrees of freedom, namely pi plus, pi minus, and pi 0. If I go to a quark-gluon plasma, you can actually calculate the energy density, degrees of freedom. So this can be calculated this way. This will be a order of magnitude higher in the quark-gluon plasma. So possibly, since I have plotted the effective degrees of freedom in the y-axis as a function of scale temperature, what is happening at the critical point or as the critical temperature is, there is an abrupt change in the degrees of freedom of the system happening here. So this pertains to the quark hadron phase transition, for which 170 MeV is the predicted temperature. And to be on the safe side, I can easily say that whereas the proton energy density is 0.17 I mentioned earlier, so around 1 GeV per Fermi Q is the quark hadron phase transition critical energy density requirement. And in my previous plots or previous slides, I convinced you that both the temperature and energy density produced at the Large Hadron Collider are way beyond the criticality expected for quark-gluon plasma formation. So now let me make little transition towards ML application, machine learning application. And before that, I must mention that to probe quark-gluon plasma, because already I convinced you that the criticality is already achieved, then I should have all the indirect probes to produce, to probe quark-gluon plasma, because this is a plasma with a lifetime of 10 to the power minus 23 seconds. I cannot have a direct probe or direct signature of quark-gluon plasma. Keeping that in mind, so both theoretical predictions and also that confronted to our experimental findings tells us there are several signatures of quark-gluon plasma, namely the suppression of charmonia, which I am going to discuss. That is strengthness enhancement, because I can convince you from the first principle PQCD calculations at the platonic level, your enhancement of strengthness can happen. And you know the strengthness is produced in strong interaction, and strength particles, they decay in weak interactions. We know this. This Then there is a jet quenching phenomena. If I have a dense medium formed, the jets, which are essentially the conical bunch of particles getting formed from the initial platonic interactions, so they can be quenched in the dense medium. This can be actually a hint of coagulant plasma or the dense medium form. And there is also collectivity, which is also um, azimuthal correlation analysis will tell me that this collectivity can also be a signature of coagulant plasma. And there are also dileptons and photons. There are several coagulant plasma signatures, but I have only noted couple of things here. And now let me migrate to heavy flavors. And from heavy flavor, I will go to charmonia suppression as a signature of coagulant plasma. And let me remind you, this charm and beauty hadrons are formed during the initial stage of the hadronic or heavy ion collisions. This is because their masses are also high, and they experience, because they are formed early in time, they experience the whole system evolution, and then they can be very good probes to understand the QCD medium. The lightest open charm is U D and C combination, which is essentially one charm, either U or D and their antiquark combinations. So that is formed through D0 and D0 bar meson. That is lightest charm containing meson, and the mass is given here. Similarly, the lightest charmonium vector meson is Jepsi, and the mass is around 3 GeV, and these are actually abundantly produced as compared to other open or hidden charms. So now if you see, so I have a quark gluon plasma. So all color objects are sitting here. UD, of course, because of their low mass, their production abundances are much higher. And this is a cartoon or the simulation to show you that Jepsi is a bound state of C and C bar. And there will be a color device screening, meaning one C cannot see the counterpart C bar to form a Jepsi bound state because of the presence of the colored objects, other colored objects like UDS. So this is essentially termed as Jepsi suppression, and this could be a signature of coagulant plasma. You can see if there is a coagulant plasma formation, so what will happen is forming a bound state of CC bar will be screened because of the presence of other colored objects. So now the first measurement came from SPS days, where the measured versus expected Jepsi was plotted as a function of the energy density of the fireball. You can see there is a suppression of this measured to expected density after around 2 GeV or so, 2 GeV per Fermi cube. And this tells me that there is a Jepsi suppression in a safe domain of criticality or coagulant plasma formation. This was also seen from the nuclear modification factor. Nuclear modification factor is a factor which is defined as the yield of certain particles in heavy ion collision, AA collision, divided by the corresponding yield in PP collision scaled to the number of binary participants. And if RAA is less than 1, so there is a suppression of particle, and if there is a RA is greater than 1, so there is no suppression, and hence there is no dense medium formation. So this nuclear modification factor, when it is plotted as a function of n part, you can see these red points are allies, the large hadron collider points, and these blue points are also little lower energy 2.76 TeV points. And this is compared with the Phoenix measurement of the RIC or relativistic heavy ion collider. You will find the suppression level is higher at lower energy, which is naively not expected. So as a consequence, we started digging inside what is the situation that high energy, instead of producing more suppression, why it is producing less suppression. Of course, both the situation is below 1, thereby telling me that all these collision species and energies, I am producing energy densities which are much higher than the coagulant plasma formation. So a new mechanism of particle production is coming up here, that is termed as a regeneration mechanism. So suppression and regeneration because of the abundance of the charm quarks. So there is a regeneration activity happening in my plasma. So suppression is because of the color screening, regeneration is because of the abundances of the charm quarks. So this competition is telling me that there is also some production of Jepsi happening because of the regeneration. That is why this suppression level at higher energy is less compared to the low energy experiment at Brookhaven. So with this, let me go to the measurement of Jepsi production in PP collision. What we have done is we look into the scaled production and scale production of this quarkonia as a function of scale production of the final state charge particle multiplicity. By the choice of this kind of ratio observables, the advantage is several correction factors in the experiment they will cancel out. And this will be easy to compare the results across the collision species and energies because I am taking only charge particle scaled multiplicity. So I can put PP, P-lead, Jinan, and the this year we are going to take data for P oxygen and oxygen. Everything can be put together in this scale. So that is why this scaled multiplicity is the new observable came up, of course, at the LHC to study this differential production of particles. So now let me show you the Alice experiment. So as you can see, slowly I am moving towards the experimental part. This Jepsi is produced or the decays to the final state dileptons in terms of dielectrons here and dimuons also. So as per our requirement, so we have the electron detector sitting at the mid rapidity versus muon detectors because more observer is necessary. So we can only put at the forward rapidity. So these are sitting at the forward rapidity. So Alice is capable of measuring Jepsi or estimating Jepsi yield at mid rapidity in the dielectron channel versus at forward rapidity in the dimuon channel. So now similar, both the measurements are done taking inclusive Jepsi. Please keep in mind, I am now discussing inclusive Jepsi and slowly I will go to prompt and non-prompt Jepsi. I am making a case. Why do I need to go for differentiating between Jepsi and Jepsi prompt and non-prompt, and what is the necessity of applying machine learning? So I am actually paving my way out. So now you can see this was part of the PhD thesis of my student Dhananjay Thakur, who did PhD at IIT Indore with me. And this paper, which I'm discussing now, is published in JHEP by Alice. And what we could see is there is a non-linearity or deviation from linearity in the behavior of forward rapidity dimuon channel Jepsi production, unlike E plus E minus, which is following a linear behavior. Of course, we studied the autocorrelation bias by taking if my signal is at the forward rapidity, my x-axis measurement should be at mid rapidity and vice versa. Thereby, these autocorrelation studies are done, whereas we found that the behavior in the particle production is different. And what bothered me on the way is I am measuring inclusive Jepsi. Keep in mind. So now the similar thing when compared with the theoretical predictions, as you can see, whatever theoretical models, theories available in the literature, when those are compared with the data, you can see there is a good degree of mismatch with the data. I'm not going to the details. You can see the Pythia, EPOS 3, percolation model, 3 Pomeran color glass condensate, CGC based ICEM model, and CPP model. So all these models are telling me none of the models are eligible to explain the production of Jepsi, inclusive Jepsi, in the dimuon versus dielectron channel come from low multiplicity to high multiplicity, and this leaves with lot of room for theory and phenomenology to tune your theoretical assumptions. So now with this understanding of Jepsi production, in our group, we try to understand with the new hypothesis of color reconnection, multipartenic interaction. So to explain this normalized yield of Charmonia as a function of final state multiplicity. So what we saw is the MPI, the multipartenic interaction based model of Pythia with color reconnection reasonably explains the data, as you can see, and we published this paper in Physical Review D, so you can have a look at this, and this is much before the experimental result was reported. And As we know that Zepsi suppression is a signal of coagulant plasma. Always the ultimate game is to look for coagulant plasma formation. The question is, do I produce coagulant plasma in proton-proton collision, which conventionally, so far, historically, is used as a baseline measurement to study heavy ion collisions. So to look for coagulant plasma signatures in PP collisions, what we did is we took a unified model where we have suppression of gypsy through color screening, gluonic dissociation, collisional damping, regeneration of charmonia due to correlated CC pair, which I explained you, and we explained that the normalized gypsy yield as a function of final state multiplicity. The behavior is explained in this framework and it is reported in EPJC from my team in collaboration with Professor Jana Alam from Calcutta. So now you can see with these ingredients in the theoretical picture, we could explain the Jepsi yield as a function of multiplicity. Does it tell me that PP collision produces a Jepsi suppression? Although I have an ingredient of suppression here, I have also the regeneration into the game. So this you have to keep in mind that based on one experimental paper, you can have several theoretical papers. Unless this is theoretically proven, still I stay at the conjecture level that we produce a proton-proton collision which produces QGP-like signals. Now, as I repeatedly mentioned, my experimental measurement and the theoretical estimation, still my last slide was with inclusive GEPSI. Let me go to separating prompt versus non-prompt GEPSI. And I should remind in the Alice experiment, the way the muon detector system at forward rapidity works. This is my collision point, and there are different observers and the tracking stations. And the difference between round 2 and round 3 is that round 3, which is ongoing, we have added a muon forward tracker, which is essentially giving me 5 points to my tracking of the muons. And this is closer to the interaction vortex. That means my secondary vortexing capability is higher in round 3, for which the data analysis is ongoing. And the work which I am going to show you next 5 to 10 minutes is on the round 2 data, where there is no MFT. I cannot go up to the primary vortex. I cannot have a secondary vortexing. So keeping that in mind, essentially this is the picture to show you that muon forward tracker is in place, and this is close to the interaction point. You can see this. This is round 3. Round 3 is ongoing now. Now the machine learning applications towards my last uh, part of my presentation is essentially based on, we have published 5 physical review D papers on machine learning. And of course, I cannot discuss all the 5 papers. I have chosen the last 2 papers which we published in 24, and these are based on machine learning. Now let me go to separating topologically this prompt versus non-prompt GEPSI. Let me define this prompt versus non-prompt GEPSI. So I have 4 hadrons. In the prompt sector, I can have direct prompt coming from the perturbative, the QCD processes, and this goes to directly produced collision. They are produced directly in the collisions. There are indirect prompts which are coming from the feed down of the higher states of Germania, and non-prompts are those which are actually produced through the weak decay of beauty hadrons. And this, to understand this topology, there is A and A is essentially the heavy ion collision. You have a prompt production of GEPSI to dilepton channel. GEPSI goes through a C tau of few microns, you can see, which is the decay length. Whereas the GEPSIs or the charmonia produced from bottom decays, so this can fly a certain distance, creating a secondary vortex. Then it will go, this is essentially the decay length of GEPSI. Then it goes to the dilepton channel. And there is a requirement of separating charm versus prompt versus non-prompt. Reason being, in Atlas experiment and Alice experiment, it is shown that this nuclear modification factor is different if you compare prompt versus non-prompt, both ZEPSI and D0. So we have worked on both the problems addressing, segregating ZEPSI prompt versus non-prompt and studying all this behavior. So now I made a case to you that ZEPSI production dynamics is not properly understood unless we separate prompt versus non-prompt, and we are doing that using machine learning. Otherwise, again I emphasize what I am going to do is I will rely on the track level properties of the particles, and the way in the experiment so far without applying machine learning it is done. You have a cocktail fitting to get prompt versus non-prompt size and properly dealing with the background. And machine learning gives me the advantage of dealing with track level properties. As you can see here, we simulated PP collisions at 13 TeV, and our predictions will be for lower energies also, but based on 13 TeV PTR data. So we trained our machine learning model using this. 20 million minimum bias events are produced. You keep in mind it is all minimum bias. Primary vortex are randomized following a Gaussian distribution because we found anybody doing experiment, the experimentalist in the audience, you also know when the day one when you plot your primary vortex Vx, Vy, Vz distribution, you find there is a Gaussian distribution. That is what also in a Monte Carlo way we introduced this thing. And we looked at exactly in experimental way, ZPSI going to V plus V minus channel. And we looked at invariant mass of dimuons, their transverse momentum, rapidity, pseudo rapidity, and pseudo proper length C tau. All these are studied in this paper. And this gradient boosting method where we use XGBoost, light GBM, and cat boost. So this essentially reducing your error through higher level of iterations, which will be discussed in length during your main school and also during the workshop when you will have the hands-on training. So here taking all these input parameters, taking LGBM, XGB. So what we studied is training and validation. The loss function plotted as a function of number of trees. You can see it is saturating around, depending upon the model, it saturates around 25 here and 45 number of trees. And this is for LGBM. And the training and validation curves are on top of each other, which you cannot distinguish. And this tells me that there is no overfitting or the underfitting. With this, so we studied the confusion matrix, which talks about the predictions given by the model. We took both LGBM and XGB here, and we found that the prediction versus true is 98% prediction is there. This 2% mismatch, like wrong prediction of prompt versus non-prompt is happening in the model. And when we study this importance score, we found that the invariant mass plays an important role in predicting prompt versus non-prompt. And the next one is C tau. So these are expected from the properties of the decay topology of these particles. So these two will make a pivotal role in distinguishing or segregating ZPSI prompt and non-prompt. So with this, with 98% accuracy in the machine learning prediction, so what we studied is the invariant yield. As you can see, the ratios of XGB, LGBM with respect to Pythia 8 true values are close to 1, and we could get up to 98% accuracy of prompt and non-prompt tagged ZPSIs. And our prediction also worked well for lower energies because our training is based on invariant mass and C tau. Those are particle decay properties and particle properties itself, and it does not depend upon the energy of the collision. So that is the beauty we saw. And we defined this FB, which is the fraction of non-prompt production. So you can see at higher PT, we expect that bottom production should go on increasing, and that bottom hadron production contributes at high PT towards Germania production, and that is what we see here. And there are some observations like how I compare with Pythia and Alice data. Of course, Pythia doesn't agree completely with Alice data; it over predicts, and you can see since the training is done on Pythia, so XGB and LGBM both are close to Pythia data. So then some other studies involving rapidity distribution, this is what we did, and this will play a very important role when our pseudo rapidity coverage will go to 8 units in the ALICE 3, when ALICE 3 will be operational from 2032. So these are some predictions where this can be worked on. And then the normalized Jepsi yield, which I talked about, that is also studied here. You can see our machine learning predictions are very exact, close to the trend, and of course the estimates of Pythia. Then going again one step ahead, if there is a Jepsi suppression, I should see D0 kind of open charm enhancement. So this is a complementary study in comparison to Jepsi suppression. So that is the reason I also studied D0, which is a mid rapidity measurement in pion kaon channel in ALICE. And here we tried to play with different model and different input variables. So we took invariant mass, pseudo proper time, pseudo proper decay length, and distance of closest approach is something which is added to the input variables here. And then we studied the importance score comparison here, and we found that the distance of closest approach and the invariant mass of k pi are playing a better role for training up the machine learning models. So now we took here XGBoost, CatBoost, and Random Forest. All these architectural discussions will happen in your subsequent discussions in the school. What I found is our model shows accuracy of 99% in separating prompt versus non-prompt D0 measure. And again, I should remind you what we followed so far is the track level properties, no cocktail fitting, no background subtraction. So this puts machine learning in the higher footing compared to the earlier methods. Believe me, when we published our first paper during 2021, when I was a some scientific associate, when I discussed that we have this paper, nobody took it seriously in 2021. Now, in Alice experiment, although we have not yet reported from the round 3 data, the machine learning applied papers, there are many groups who are working on our ideas of applying machine learning in these kind of discussions. So now the transverse momentum spectra of D0, as you can see, there is a very good overlap or matching, and machine learning is doing a good job here. And similarly, we studied the rapidity spectra. So I'm not discussing the in-depth physics of all these things, but of course, during 2032, when our rapidity coverage of ALICE 3 will be higher, all these things will be studied in the experimental data. And what is more important is this non-prompt to prompt D0 ratio. And we see the ALICE data from a different cocktail method, that is when compared to Pythia. Of course, Pythia is a theoretical model, so there is little mismatch, but Pythia machine learning trend model of XGB is essentially predicting up to 99% accuracy. So now let me summarize this discussion. What I presented to you is the topological separation of D0 and Jepsi produced in PP collision at LHC using different machine learning models. Before this, I introduced, with the aim of producing quark-gluon plasma in the laboratory, all sort of basics, so that in subsequent lectures, anywhere you attend a conference, you will be in a position to understand some of the basics if you happen to be little off the quark-gluon plasma field. Different boosted decision tree based classifiers have been used to tackle this problem. The model is trained at 13 TeV, and this makes a reasonable prediction at low energies. ML approach to separate prompt non-prompt production can be very useful in experimental analysis, which many people are doing. We are also in the game of doing that after verifying the capability in this process. A proper separation of prompt and non-prompt can reveal about different multi-particle production dynamics when studied in a more differential way to understand multi-particle dynamics. And what I discussed with you is these two papers published in Physical Review D last year. But I am not discussing with you, and you can actually follow uh, the application from these three papers. Again, all are Physical Review D. The first paper was in 21, then 22, 23, and then we published 24 too. And we are writing one more this year. And I think I must thank you that you listen to me possibly carefully. Possibly is important because I don't see you for last 1 hour. Thank you.
Thank you, Raghunath. It was very nice overview and very encouraging that invites people to this quark-gluon plasma related physics issue where DBTs and other models possibly can be used. Hopefully, we'll hear more about it in the main school from you. And I open the floor for questions so people can either raise a hand so I can allow them to speak, or they can put in the chat box.
Yeah, maybe you can moderate that. The reason being I cannot see
Yeah,
anyone.
yeah, no problem. So that's what I'm saying. So if there are any question, comment, please put in the chat box, or you can just raise your hand and I can ask you to speak. Do we have? Looks like we don't have any questions from the students. Raghunath, if you don't mind, I have a simple question,
Yeah.
which is that in your data, I mean, even in your experimental simulations, you talk about the pion multiplicity and kaon multiplicity. So this is possible to identify those particles because they are typically within the few GeV of transverse energy, right? Transverse momentum.
Uh,
The charge hadron identification is possible, which is not possible at LHC.
SATs have done without PID. Of course, we can go to 100 GBs.
Uh,
uh, Atlas and CMS they can go to higher PT. Our
yeah,
low PT is better in Alice.
yeah, yeah,
And if you go to particle identification, for example, pion, kaon, proton.
yeah,
So because of the d by dx, the Bethe-Vlock formula merging around 1 GV.
yeah, yeah,
So if you recall that we need time of flight and other detector information track matching should be combined together
yeah.
to take us to few GVs. Once you
QG.
identify pi and kaon.
Yeah,
If you do not identify, of course, the reach is much higher,
uh,
but Atlas and CMS are higher than Alice reach.
yeah, yeah. That because they are have different setup. So in your setup, so this is basically PT of. Are you going less than 1 GB as well in your data collection?
I think we start around 150 MeV.
150 MB. That's quite
Yeah,
impressive. Yeah, because I think at least CMS cannot even record if it is less than 1 GB of PT.
yeah.
I mean, it can record, but usually it gets thrown out as a noise.
Yeah,
But
our
it goes
low
perhaps
PT reach
30 to 10
is better, and that is even getting better in round 3 and
Uh,
in Alice 3 because we are sitting now closer to the beam pipe.
yeah,
Our ITS is now upgraded,
yeah,
and in Alice 3, which is starting around 2032, so
yeah.
the planned detector will be all silicon. TPC will
Uh,
be taken out.
okay,
Then the inner tracking system will be like a paper,
yeah,
silicon paper. It will be wrapped around the beam pipe.
okay,
Okay. So our low PT measurement focusing on heavy flavor and dileptons,
yeah,
photon and dileptons. So that will be much more enhanced measurement will happen in the coming days.
okay. That's good. Yeah. So thank you, Raghunath, for this wonderful exposition. And so I'll request you to stop sharing the screen.
Yeah. Thank you. It was my
Thank you.
pleasure. And I don't know
Thanks a
for the
lot, and
student.
hopefully see you in Kolkata. Yeah.
Sure, sure. Thank you. Thank you. Uh,
So I will ask student to take about 5 minutes of break and be back here at 5:47, where we will start with Satyaki Bhattacharya's seminar. This 5 minute break is important. I have realized that student has a finite you know, reception capacity. So this 5 minute break will be very, very useful. So don't go away. Just take a 5 minutes of break. I'm gonna stop the recording and I'll start it again.
yeah. Thank you. Thank you, all of you.
Thanks. Thanks a
See you
lot.
sometime. See you sometime physically. Yeah? Bye.
Thanks.